You're used to the idea of stereoisomerism in organic chemistry, either in the form of Ez isomerism, which remember we often call Cis Trans Isomerism in alkenes, which results from the lack of rotation around the double bond in alkenes, or optical isomerism, which results from the presence of chiral centers. So it turns out that both of these kinds of stereoisomerism can occur in transition metal ions as well, and you need to know about both of those situations. So we'll talk first about cis trans. We don't use Ez in the case of complex ions, so we're only going to use the cis trans nomenclature. And this kind of isomerism is a feature of situations where you have squares, so either a square planar complex or an octahedral complex, where of course any 4 out of the 6 ligands are arranged at the corners of a square. And in that situation you can see quite easily how cis trans isomerism is possible. So this is a very famous example of cis trans isomerism in a square planar complex. So what you've got here are 2 forms of the same complex, which has a platinum 2+ ion and 2 chloride ions and 2 ammonias. So the total charge on this complex is 0 because you've got 2+ on the platinum but 2- from the 2 chlorides, no charge on the ammonias. So these are neutral complexes, and so they exist as sort of compounds in their own right, but they have this structure of transition metal complexes. And you can see there are 2 forms of this complex, even though you've got the same metal ion and the same set of ligands. And they differ in terms of the angle between the 2 like ligands. So if we focus on the 2 chloride ions, you can see in this version the angle between them is 90 degrees, which has the result that they're sitting next to each other on the same side of the complex. But where the angle between 2 ligands is 90 degrees, that's defined as the cis isomer. Here, the 2 chloride ions are on opposite sides of the complex, and that means the angle between the 2 platinum-chlorine bonds is 180 degrees, and that's defined as the trans isomer. So you need to learn this specific example as a case of cis trans isomerism, and these 2 compounds don't change one to the other very easily, so you can prepare them as individual compounds, and this one won't just sort of gradually change into that one. They're quite stable in their separate arrangements, and they have different properties. And the one you need to know about is that the cis isomer specifically, this compound is called Cisplatin, and it's the isomer which has the 2 chloride ions in the cis orientation, so 90 degrees apart. And this one has this important medical role, that it's used in the treatment of cancer. You don't need, again, to know any real detail about that, but you need to know that it works by binding to DNA, and by doing that it prevents cells from dividing. And of course, since cancer is a disease in which cell division runs out of control, stopping cells from dividing is an important therapeutic strategy. So you just need to know that this particular isomer, the cis form, has this anti-tumor activity, and the trans form doesn't. So cis trans isomerism matters because it gives these different properties. If you have an octahedral complex, then you can again get cis trans isomerism. So here's an example of chromium forming complexes with a mixture of 4 ammonias and 2 chloride ligands. And you can see in this example on the left, the 2 chloride ligands are next to each other, and that angle, remember, is 90 degrees. It doesn't really look like 90 degrees in the picture, but it is. So those 2 chloride ions are 90 degrees apart, so that's a cis isomer. Here the 2 chloride ions are on opposite sides, so they're 180 degrees apart, and therefore that's a trans isomer. So you can get that kind of isomerism with two different isomers if you have two ligands of the same type. If you have three ligands of the same type, then again you can get cis trans. So here, this is the cis isomer, and you can see you've got three chloride ligands, and if you choose any two of them, doesn't matter which two you choose, the angles between them are always 90 degrees, and that's the characteristic of the cis isomer. Here, although you've got this pair, which are 90 degrees apart, you can find a pair which are 180 degrees apart. And it's having that pair 180 degrees angle between them that defines that as the trans isomer. So these are the two simple situations where you have unidentate ligands where you can get cis or trans isomers. But actually, where this kind of isomerism is most commonly seen is when you have bidentate ligands. So here's an example of a complex with two diaminoethanes. Remember this molecule, which has NH2 on both ends, and then a pair of CH2s in between, is called 1,2-diaminoethane. And you've got two of those, and then two chloride ligands in this complex. And again, if you just focus on the unidentate ligands, that's the easiest way to define whether it's cis or trans. The two unidentate ligands, the chlorides, are 180 degrees apart, so that is the trans isomer. Here again, you've got the two bidentate ligands, the diaminoethanes, and the two chlorides, but the two chlorides are 90 degrees apart, and so that's called the cis isomer. And again, those exist as separate ions that don't easily change one to the other and back again. So if you have to draw those, the easiest way to do it is to draw on the two unidentate ligands first. So if you know you want to draw the trans one, draw the two chlorides on first, and then you can just fit the bidentates around them. But because the angle between the unidentates is what defines whether it's cis or trans, if you put those on first, so 90 degrees in this case, you just draw them next to each other like that, and then it's easy to fit the two bidentate ligands around them. Optical isomerism is the other kind of stereoisomerism, which again you know already from organic chemistry, so you're used to looking for chiral centers in organic molecules. You can also get chiral complex ions, and again you just need to first of all know where to find those, what arrangement of ligands will cause chirality, but also you've got to practice drawing them. And in terms of properties, it's the same story, that because they're non-superimposable mirror images, they have identical properties except when they interact with other chiral things, like other chiral molecules. So here's the first example of that. So here you've got a complex formed from cobalt interacting with three diaminoethanes. This is cobalt 3+ in this case, with three diaminoethane ligands. So you can see the three bidentate ligands, so it's a coordination number of 6, but three ligands arranged around it. And it depends really how good you are at visualizing things in 3 dimensions, whether you can really see this, but these two are mirror images of one another. So you can imagine a mirror line down here, and this one is a reflection of that one in the mirror line that runs down the middle like that. The bottom line is that for exam purposes it doesn't really matter whether you can see that they're mirror images or not. You just have to remember that that's the case. And the way you draw them is just use exactly the same strategy that you would do with the organic case. So you could, if you like, even draw the mirror line in like that, and then draw them on one side with the three ligands in whichever orientation you like, and then do the reflection operation in that mirror to draw the one on the other side. And then just make the statement, oh, these are non-superimposable mirror images, and they're therefore optical isomers of one another. So you can get that with 3 bidentate ligands, and then with 2 bidentate ligands. Now this story is probably the one that's come up in exams more often than any other one, because with 2 bidentate and 2 unidentate ligands you get both kinds of stereoisomerism, and so it makes a very nice kind of catch-all story for exam purposes. So this is an important one to make sure you know. So we've already seen that if you have 2 diaminoethanes and 2 chloride ions around a metal ion, for example, that you can get Cis Trans Isomers. So this one is the trans form, because remember that's defined by the 2 unidentate ligands, the chloride ions, having their dative covalent bonds 180 degrees apart. So that's the trans isomer. And that one I think you can see just by looking at it that it's symmetrical. The mirror image of that would be identical, and you can see that because it's got a mirror plane down here. It's also got a mirror plane horizontally across there, and indeed down the middle in the plane of the screen, as it were. So it's highly symmetrical, and therefore it doesn't have a non-superimposable mirror image. Okay, it's just got one form. But if you have the cis form, which is the one at the bottom, where this time the 2 chloride ions are 90 degrees apart, so this is the cis form, these 2 are non-superimposable mirror images. So again, it's a case of the mirror line is down here, and this one is the mirror image of that one. So what they will quite often ask you is why there are 3 stereoisomeric forms of this complex. If they just give you this sort of formula like you have at the top, they can write it out like that, and then just say, why does that exist in 3 different forms, and draw the pictures to illustrate it. And you just have to say, right, there's the trans form, and then there are these 2 stereoisomeric cis forms. So that's all there is to stereoisomerism. It takes a bit of practice drawing the pictures, but really that's all you need to learn to do, is to name the different kinds of isomers, draw the pictures, and learn the little story about cisplatin and its use in medicine. And then you can practice that by doing questions 7 to 10.